So, hello everyone, and thank you for the opportunity to talk at World of Groupcraft. My name is Giorgio Mangioni. I am a second year PhD student at Heriot-Watt University, and today I wanted to talk about an amalgamation criterion for certain geometric subgroups of mapping closed groups. So, we start with the basic of what is a surface. We take a compact orientable connected surface, possibly from which we remove a finite number of punctures. And we define its mapping class group as the group of self-homomorphism from the surface to itself, fixing the boundary pointwise up to homotopy. So if two mapping classes are homotopic, we deem them equal in this group. So if you have S and a subsurface U, which is closed into the bigger one, then what you can do is that you can take a mapping class supported on U and you can extend it to the identity on every connected component of S minus E. And this gives a homomorphism from the mapping class group of U to the mapping class group of S. And a theorem of Parison-Wolfson says that this map is injective if and only if the complement of U contains no annuli, so for example this annulus is forbidden, nor this with at most one puncture. So we have to forbid both the right disk, which has no punctures, and the left disk, which just has one puncture. So if none of these bad cases happen, then we say that the mapping class group of U is a geometric embedded subgroup of the mapping class group of S. And so our goal is to find, to state a theorem saying when two such geometric embedded subgroups generate an amalgamated free product over their intersection. But first we need another tool, which is the curve graph, as introduced by Harvey in 1981, which is the simplicity graph in which the vertices correspond to the curves on the surface, and where two curves are adjacent in the graph if and only if they are disjoint on the surface. So for example, the red and the green curve are disjoint on S, so they're connected in the graph on the right, while for example the red one and the blue one are intersect on the curve, on the surface, sorry, and so they're disjoint in the curve graph. So here's the setting of our theorem. Take two geometric embedded subgroups of a mapping class group supported on two closed surface U and V. Here we did not represent the surface but just their boundary. And notice that U and V have some common boundary component, which is this gamma here, this curve here. And we require that when looked in the curve graph of S minus the boundary, the common boundary, the boundary of U and the boundary of V are very, very far away. Meaning that they entangle, they overlap quite a lot, and they have a very, very messy intersection. So the theorems, which is forthcoming, I hope to release it in short, says that if you pass to finite index subgroups inside the geometric embedded subgroup, you can assume that the subgroup generated by this finite index subgroup in the mapping class group is just the amalgamated free product over their intersection. And the intersection is exactly the Dehn twist flat supported on the common boundary multicurve. So in this case here, the intersection would be the cyclic subgroup generated by the Dehn twist along the curve gamma. So this result should be compared with a result of Leininger and Reed, which is about a combination theorem for which subgroups of the mapping class group. And this is very similar because in both cases you have two subgroups of mapping class groups and you want to show that they actually generate an amalgamated free product over Dehn twist flat along a common subcurve, which in this case is the boundary curve gamma. However, our result is kind of different because while Leininger subgroup, which subgroups are made of pseudo-knobs of elements away from the intersection, In our case, we have two reducible subgroups, which because the mapping class of U clearly fixes the boundary curves of U, so it's reducible in the mapping class group of the whole surface. So what's the idea behind the proof? Well, first you notice that you can find a finite index subgroup as in the statement, so that whenever you take an element which is not support just a multi-twist supported on the common boundary, then you can find a subsurface of U where this element acts loxodromically. Say it has very large translation on the curve graph of this subsurface, and by how we chose the non-common boundaries of U and V, we chose them to be very far away, very entangled. What you can see is that if you have A in one subgroup and B in the other, and not in the intersection, then these two subsurfaces must wildly overlap as well. So you have a mapping class which translates a lot in the curve graph of one surface, a mapping class that translates a lot in the curve graph on the other surface, and these two subsurfaces are transverse. So you have, and that's, let's say, the first and second step to get to the actual proof. Well, I have to say, for who knows what I'm talking about, that this result is actually quite more general and applies to subgroups of hierarchically hyperbolic groups, which include mapping groups but are quite a wider class, including, for example, right angle arting groups, a lot of arting groups, a lot of um, fundamental groups of three manifolds, for example. And what you can also show is that if you have two subgroups satisfying some properties which almost amount to have these two subsurfaces which are transverse and each of the elements translate very far on the corresponding subsurface, then you can also preserve some convexity properties of your subgroups, such as hierarchical quasi-convexity or strong quasi-convexity or something like that. Meaning that if the two subgroups you start with have this convexity property, then the subgroup they generate still has this property. So if someone is interested, please send me an email and we can talk about it more. So thank you for listening and see you next time.